So next polar graph that we're going to graph is a lemicon. These are always when you have the equation r equals a plus or minus b sine of theta, or r equals a plus or minus b cosine of theta, where a and b are both positive. Honestly, I don't really remember what shapes these are. I just, make my chart and connect the dots and increasing theta, and it gives me the correct shape. So we'll start by testing for symmetry. So hopefully we can lessen the number of thetas we have to choose in our r theta chart. We'll make our little chart or polar axis. Theta equals pi over 2, and then the pole, the three symmetries we're testing. For the polar axis, this is where we replace theta with negative theta, and we typically are using our negative angle identity to simplify this. What do we know about cosine of negative theta?
It's just cosine.
It's just cosine of theta. So when we simplify, we get our original back. So this will definitely have symmetry with respect to the polar axis. To test our symmetry with respect to the line theta equals pi over 2, we're going to replace both theta and r with the opposite. So negative r equals 1 plus 2 cosine of negative theta. We'll use our negative angle identity to simplify the right side, and that turns into just plus 2 cosine theta. And then we want to see if we can turn it into the original. We could try dividing through by -1, but that's not going to give us the original. So this is a maybe. And then last but not least, testing symmetry with respect to the pole. Here we're just replacing r with negative r. That'll give us our diagonal symmetry. Can that be turned into the original? No, that's what we had in the last step. So this one's a maybe as well. Our graph is only for sure displaying symmetry with respect to the polar axis. Our polar axis coincides with the x-axis. So that means that when we make our r theta chart, we only need to choose thetas from either quadrants 1 and 2 or 3 and 4, either above the axis or below the axis. I chose to choose theta in quadrants 1 and 2. So we chose our theta, and then we just plug it into our formula, and we get our decimal approximation. So now let's plot these points. Starting with, I know I always say it backwards because R comes first in the ordered pair, R theta, but you start with your angle theta and then count out your R's. So technically the point is 3, 0, but I always think of it as 0 for my angle, then 3 for my R. Next, we're going to pi over 6, and we're going out 2.73. Remember that our lines are 15 degrees, so we're going to have to go 2 of them to get our pi over 6. Pi over 4, just shy of 2.5. Pi over 3, we're at 2. pi over 2, we are at 1. 3 pi over 2, 0. Next, at 3 pi over 4, we notice that we have a negative r value, so that means that we're actually going in the opposite direction, back this way, negative almost a half. At 5 pi over 6, again, that negative r value, so we're going to go in the opposite direction. Take us over here. And at pi, again, negative r value, so we're going in the opposite direction. We're going to be right here. Questions on any of the points we plotted? Well, our test showed us that this is going to display symmetry with respect to the polar axis right here. Do we currently have the mirror image on either side of our polar axis? No, we don't, right? I don't have matching points on either side. So now I'm ready to create matching points on either side of this line. And we're just going to reflect them. And then the little ones on the inside. And now we have the mirror image on either side, and we're ready to draw in our graph. I like to go in increasing theta. So we're going to start out here at the 3, 0. And there we go. Questions at all? Next up are Rose curves. You have a Rose curve when you have a single term, no plus a constant, but your argument is something other than theta, so 2 theta, 3 theta, 5 theta. If n is even, then the rose has 2 n petals. If n is an odd number in the argument, then you have n petals. Again, that's not really something I tend to remember. I feel like you see it when you plot the points and draw it in for increasing theta. But if that's something you want to memorize, please feel free to do that. I'm going to start by testing for symmetry. So for polar axis, we're replacing theta with negative theta. R equals 2 cosine of 2 times negative theta. So that's 2 cosine of negative 2 theta. Our negative angle identity tells us that cosine of negative is just the same as cosine. So this turns into R equals 2 cosine 2 theta, which is our original. So this is a yes for sure on symmetry. For theta equals pi over 2, we're replacing both. Cosine of negative 2 theta simplifies into just cosine of 2 theta. We could divide every term by -1, but that's not going to give us the original, so this is just a maybe. And then lastly, the pole, we're just replacing r with -r. And as we saw on the previous test, this does not turn into our original even when we try dividing by -1. So this is also a maybe. We only display symmetry with respect to the polar axis, which coincides with the x-axis. So we're either looking for the top 2 quadrants or the bottom 2. Again, like the previous example, I chose the top 2 coordinates, 1 and 2. So I chose theta from 0 to I. Plugged it in and got ourselves some ordered pairs to plot. So let's plot them. 0, 3, pi over 6, 2, pi over 4, 1, pi over 3, 0. Pi over 2, we end up with a negative r value. So let's make sure that we're going in the opposite direction. Two pi over 3, we're back at 0. 3 pi over 4, out at 1. 5 pi over 6, out at 2. And pi, we're out at 3. Questions on plotting any of the ordered pairs? Our test told us that this graph is symmetric about our polar axis here. Currently, we do not have the mirror image on both sides of this line, so we want to reflect our points to get that mirror image. There we go. Now we have our mirror image, all the rest of our points, and we're ready to draw in our graph. Again, we want to go in increasing theta. So here's where we started out at 0. And then it looped down, and then it came back. Then our theta went out here. And now we need to draw in the mirror image on the other half. There we go. We have a rose curve with 4 petals to it. And you'll notice that our argument was 2 theta, and in our definition it said if n was even, we would have 2 n petals. Oh, we did end up with that with our 4 petals. Questions at all? Last one, this is when we're of the form r squared equals a squared sine of 2 theta, or r squared equals a squared times cosine of 2 theta. Oh, we'll test for symmetry. For the polar axis, we're replacing theta with negative theta. Using our negative angle identity, we know that sine of negative 2 theta is equal to sine of 2 theta. I'm sorry, negative sine of 2 theta. So we end up with this negative out in front. And that is definitely not the original, and dividing both sides by -1 is not going to get us to the original either. So this is a maybe on the symmetry. Next, theta equals pi over 2. Here we're replacing both. That's negative r squared equals 4 sine of -2 theta. Squaring a negative gives us a positive, and our negative angle identity tells us this turns negative. And we're back to what we had in the previous test, which we were not able to turn into the original, so this is maybe. And then for the pole, all we're doing is replacing r with negative r. Squaring negative r, we get positive r squared. And that is our original, so this is a yes. This means that we have diagonal symmetry. Oh, we need to get 2 of the quadrants that are adjacent to each other, and then we will reflect diagonally to get the other points if they're not automatically there. Oh, you'll notice that my chart this time is a little bit more drawn out because I chose my thetas and I chose first and second quadrant. And then I plugged them into my equation, but my equation is solved for r squared. So I then had to take the square root of that answer to get my actual r value. All right, so we've got our points. Let's plot them. We're going to 0, and then our r is 0. Pi over 6. 1.86. At pi over 4, we're up at 2. At 3 pi, we're back to this 1.86. And then at pi over 2, we're back to 0. At 2 pi over 3, because r squared yielded a negative number, when we took the square root of that, we got something that was imaginary, and that happens 3 times in a row. And then once we get to pi, our r value is back at 0. So this is all we have from our xy chart. But we remember that our graph has this diagonal symmetry with respect to the pole. So I'm going to extend each of these points diagonally. And this is actually kind of nice, rather than when we do symmetry with respect to the origin. When we're in rectangular and it's hard to see, like we can actually just follow the line across to know where that symmetry goes. I'm going to do that one first because it was on 2. And then the ones on either side at 1.86. And then 0. And now we're ready to draw in our graph. I'd like to do it in increasing theta. So we started at 0 and came up and then back to 0. And then back around. Looks kind of like an infinity symbol. That's our landscapes. Question at all on graphing polar? Or
How do we know what set is like for the table to pick? Because like in some other examples they were different.
Okay, so it depends on the symmetry that we concluded. Let's see. All right. So our first one had symmetry with respect to theta equals pi over 2. That coincides with the y-axis, so it matches on the left and the right-hand side. So when you choose your theta, you either want to choose this side and do these 2 quadrants, which is what I did, or you could have done these 2 and then flipped it over to get the other one. So you figure out what you're symmetric about, and then you're going on either side of that. In the next 2 examples after this one, we had symmetry with respect to the polar axis. So symmetry with respect to this line. So when you're choosing your thetas, you either need to choose the thetas above the line and reflect down, or choose the thetas below the line and reflect up. And then in this last example, we were symmetric with respect to the pole. So that's the diagonal. So you're going to get any 2 quadrants that are adjacent to each other and then reflect diagonally. Did that clarify it for you?
Yeah, thank you.
Anybody else? Anything on polar before we get to vectors? All right. So vectors here, I just got a bunch to read. Or you know what? Why don't I just pause and you guys read for a few minutes? Because there's like 5 pages of nothing but stuff to read. So why don't you guys refresh yourself and read that, and then I will field any questions on that, and then we will actually do the problems on page 239 when we come back. So basically, vectors show both magnitude and direction. If it's going in the opposite direction, then it has an opposite angle to it. All the scalar property products. Basically, vectors just follow all of our properties of real numbers. It's associative, it's commutative, it's distributive. You have your additive identity, your additive inverse. A vector can be represented by a point, or it can be represented in our AI plus BJ form, where we're using unit vectors, having both a horizontal and vertical component to it. The magnitude of a vector is just an application of the Pythagorean theorem. It's always the square root of a squared plus b squared, and our direction angle satisfies SOHCAHTOA. Tangent of theta is going to be equal to b over a, and then our magnitude, because it is a length, of course, it's always greater than or equal to 0. The only time our magnitude is 0 is when we have the 0 vector. A vector in the opposite vector is going to have the same magnitude. So let's find the magnitude and direction angle for our given vector u. The magnitude of u is going to be the square root of a squared plus b squared. So that's going to be the square root of 625. So our magnitude is 25. And then our direction angle, we're using tangent of theta equals b over a. So we'll have to use inverse tangent here. And our direction angle, not always, but frequently we use degrees instead of radian measure. When we put this into our calculator is using our real definition of tan inverse, which is either from negative 90 to positive 90. So our calculator spits out for us negative 73.47 degrees. So that puts us in quadrant 4, but if you look at our vector and think of it like an ordered pair, negative 724 is going to put us over here in the second quadrant. But our direction angle that our calculator gave us is in the 4th quadrant. So to get us to the 2nd quadrant, all we're going to do is add 180 degrees to get us from over here to where we need to be. We end up with a direction angle of 106.26 degrees. Questions, anybody? All right, why don't you guys try the next one? Plugging in for our magnitude. Did everybody get 16?
Yeah.
Yeah.
And then for our direction angle, we end up with theta being tan inverse of -1. Our calculator is going to spit out negative 45 degrees. So we want to double check that's in quadrant 4. We want to make sure that our vector is actually located in quadrant 4 and we don't have to adjust it. And yes, it is. So theta equals negative 45 degrees, or it would be acceptable if you wanted to change that into a positive coterminal angle of 315 degrees. That'd be fine too. Questions, anybody, on finding the magnitude or the direction angle? All right, so we have our operations on vectors. If you want to add 2 vectors, you just add your horizontal components and then your vertical components, and that'll be your new vector. If we're multiplying a vector by a scalar, all we do is distribute that scalar to each component. To get the opposite vector, all you do is distribute a -1 in, change the signs of your 2 components, and subtraction, well, that's just an application of addition, adding the opposite, but basically we're just going to subtract the horizontal components and then subtract the vertical components for our difference vector. So let's try some operations. To find u minus v, all we're going to do is subtract our first components, our horizontals, and then subtract our second 2, our vertical components. This gives us the vector -6, 2. For part B, to find -5 times vector v, all we're going to do is distribute that -5 to our components for vector v. That'll give us -20, -15. And then for part C, it asks us actually to do both things, right? We have scalar multiplication and addition and subtraction happening. We always follow order of operations, so we'll do the scalar multiplication first, and then the addition and subtraction second. Multiplying 2n to u, that's going to give us -410. V just stays as it is. And then for the next one, see, we got a -6 in front. I would totally distribute the negative with the 6 so that I didn't have subtraction in between my vectors. It's going to give us -24 and -18. And now we're just adding these three vectors together. So we'll add our three first components and then add our three second components, and we get the vector -24, -5. Questions, anybody? The horizontal and vertical components of a vector can be defined. A equals the magnitude of our vector times cosine, and our component B is the magnitude of the vector times sine. And that just comes from, you know, SOHCAHTOA, if we looked at our diagram. So let's find the horizontal and components of some vector v if alpha is the angle of inclination from v from the horizontal. So all we're doing is plugging into those formulas. A is going to be equal to 26 times cosine of 50 degrees, and then our component B is going to be 26 times sine of 50 degrees. And that will have to pop into our calculator and get a decimal approximation since 50 is not on the unit circle. So let's round to the nearest hundredth. For A, we'll get 16.71, and for B, 19.92. So to write this in vector form, we can either use our angle brackets, which is typically my preference, or we can use our AI plus BJ notation, and it would look like 16.71 I plus 19.92 J. Questions, anybody? All right, well, on to applications of vectors, which I think is the best part for sure. So here's some, we know that frequently we use parallelogram rule. All right, you read that when you're looking for the sum of two vectors, aka the resultant vector, there's two different techniques where we can put the beginning of the second vector at the end of the first vector and then create a triangle, and that's our resultant vector. Or what happens more frequently in applications is that both vectors are starting at the same place because frequently we have two forces on a single object. And in that case, we use parallelogram rule, where we're going to draw a parallelogram based on our two vectors, and then the resultant is the diagonal of that parallelogram. So here's some things just that we need to remember about parallelograms. It's a quadrilateral whose opposite sides are parallel and equal to each other. The opposite sides and opposite angles of a parallelogram are equal, and adjacent angles are supplementary. I always feel like that's the part that we don't tend to remember from geometry. And the diagonals of a parallelogram bisect each other, but they don't necessarily bisect the angles of the parallelogram. That only happens in a square. So let's check out this first example. Two forces of 19 and 32 newtons act at a point in the plane. An angle of 118 degrees is formed between the two forces. Find the magnitude of the resulting force, and we'll round our answer to the nearest hundredth. A good diagram is always super important. So here's my point in the plane. I'm going to put my first vector totally horizontal. Make that one the 32. And my other vector is 118 degrees from that. So if that's 90, my other vector is maybe like right here. And this one is 19. Now we're ready to create our parallelogram. So that's four sides equal in length, opposites are equal in length, and parallel to each other. And our resultant vector is then going to be the diagonal of this parallelogram. We need to use the fact that adjacent angles in a parallelogram are supplementary. So if I know that this angle is 118 degrees, then this angle here is going to be its supplement. Which is 62 degrees. And I also know that my opposite sides are congruent, so I can label those sides as well. And now I'm ready for a breakout triangle. And I'm going to break out this triangle right here, because we're trying to find that black vector there. With the information we have, what technique are we going to need to use to find that side X?
Side angle side.
I agree, it is side angle side. What do we use to solve side angle side? We're either looking for law of sines, law of cosines.
Law of sines.
Do we have a known pair?
No.
No, we don't. So we can't use law of sines. But I do have three sides and one angle, so we can definitely use law of cosines. Law of cosine says that x squared is going to be equal to 19 squared plus 32 squared minus 2 times 19 times 32 times cosine of 62 degrees. And as always, I would just put that whole thing once in my calculator. And then round to the nearest hundredth. So if somebody could pop that in their calculator, that'd be great.
I got 28.53. Is that what everybody else got?
Sounds good to me.
Yeah, that's what I got too.
And our unit would be newtons.
Yeah.
Great questions. So typical, such a typical kind of problem. This next example is going to involve the equilibrium. The equilibrium is the vector that's opposite the resultant vector. I always think of it like a counterbalance. You see this in animals all the time. Animals that can jump really far, they always have a super long tail going in the opposite direction to balance them. So our equilibrium is just the vector that's opposite of our resultant. It kind of keeps things balanced. The two rescue vessels are pulling a broke down motorboat towards a boathouse with forces of 840 pounds and 960 pounds. The angle between these forces is 24.5 degrees. We want to find the direction and magnitude of the equilibrium. We'll round our answer to the nearest hundredth. Oh, you got to find the resultant first, and then the equilibrium's just going in the opposite direction of that. All right, so to draw my picture, I'm going to put one of my vectors right on the horizontal. Here's my boat. So that'll be my 840 there, and then my second one, 24.5 degrees. I know this looks way more like 45, but I felt like if I made it too small, we wouldn't be able to see it. And then we'll create our parallelogram. We'll use the fact that our adjacent angles are supplementary, so that makes this top angle here 155.5, and we are looking for this resultant vector here to start. I'm going to break out this top little triangle. Trying to find that side X again. So once again, we have this side angle side. I don't have a known pair, so that tells me I'm going to have to use law of cosines. X squared is going to be 960 squared plus 840 squared minus 2 times 960 times 840 times cosine of 155.5. Take the square root of that and plug it into our calculator. Let's round to the nearest hundredth. Somebody gets an answer for that.
I got 1,759.20.
That's what I got.
What did you say? Yeah, that's what I had, what she's writing.
All right, and then our unit is pounds. So that is the same as the magnitude of our equilibrium because the two are the same, but now we need to find the direction of that equilibrium. So we want to find the direction angle of our resultant vector, and then we'll need it to go in the opposite direction from that. So we'll add 180 degrees once we get that to get it going in the opposite direction. So we're looking for this little angle here. I guess I'll call you alpha. Since we now know what side x is, you could use law of sines here. Or we can use law of cosines. It doesn't make a difference. A law of cosines I typically like, even though I know it's a little bit more writing. I usually like to use that because then you don't ever have to worry about the ambiguous case. So 840 squared equals 960 squared plus 1759.2 squared minus 2 times 960 times 1759.2 times cosine of alpha. Because I'm already working with a rounded value, 17.59 or 1759.2, I would do my best to try to plug this all in my calculator at one time. Like, you know, subtract those two over, divide by this stuff, and then do inverse cosine to get my alpha, just so I wasn't rounding and rounding and rounding. If we do that, we should get that alpha is equal to cosine inverse of 840 squared minus 960 squared minus 1759.2 squared divided by -2 times 960 times 1759.2. And I'd plug that in my calculator all at once, making sure that you're putting your numerator in and denominator in parentheses. Anybody get an answer?
11.42.
Anybody else get that?
Yeah.
All right, so to get the equilibrium, we need to be traveling in the opposite direction. All right, but I want to talk about how to label this. So what we found is this right here. Right? That's the whatever number you gave me, the 11. The equilibrium vector, right, is this one. So we are looking for actually either this angle, right, or this angle. And I lined up the green vector on the horizontal because our direction angle is supposed to be based off, you know, it's the angle in between the horizontal and this. So we can't just add 180. That's not going to get us right over there. So if this part was, what'd you say it was? 11.42, and I know this total angle here was 24.5. What does that make this blue part here? We just need to do 24.5 minus,
12.25.
what is it?
12.25.
So we're in here, and this I put in here for an example for.
Okay, that cannot be 12.25. We're doing 24.5 minus this 11.42.
I got 13.08.
Oh, I thought you were just dividing it in half.
All right. So it's this, and now we need to get like here. So if this is 180 degrees, we actually need to add the 180 degrees to 13.08 so that we get from the horizontal, which is the green, over there. Right? Does what I'm saying make sense to everybody?
Yeah.
Equilibrium is this over here. But what we found was just this angle here. To get our direction angle, we need to add 180 degrees to the part of the angle that is from the horizontal, which is that 13.08 degrees. I guess I'll label that beta. All right, so beta is going to be this 13.08 degrees, and now we're going to add 180 degrees to go in the opposite direction. So our direction angle, which I'll call theta, for our equilibrium vector is going to be 193.08 degrees. Questions on parallelogram rule? All right, that's a perfect place to stop. We'll pick it up on Friday doing applications of vectors, where we'll do the applications where we're pushing things up an incline, and then some general applications, and then we will move on to do dot product. And we are almost done with this unit. All right, anybody got any questions about anything?
No.
Thanks, Jordan. That's cracked me up. All right, well, if nobody has any questions, I'll have my video off. Nobody has any questions, then I will see everybody on Friday. Have a wonderful day.
You too.